This is lesson 9, or unit 9 actually, lesson 1, looking at trig equations and identities. Some of the work that we do here will look very familiar, and some of it will be new, and some of it will be a combination of all kinds of good things. So the first two questions that are presented as review are very much a part of our last unit, using our calculator to go inverse sine and find the angles, doing a little bit of algebra perhaps on the other one. 3 secant x is equal to 5. Secant x is equal to 5 over 3, recognizing that secant is 1 over cosine of x is equal to 5 over 3. And then doing a little bit of algebra. So 1 divided by 5/3 would be equal to cosine x, or cosine x would be equal to 3/5. And we know how to do that on our calculator. The solutions that we would obtain here for a very narrow window, from 0 to 2 pi, or from 0 to 360. And we're actually looking to obtain general solutions that are true for the reals. So we're going to check that out graphically. Going to skip over to one more page where we get to look at a really large graph. So here we have the sine of x equaling its graph as we're used to it from our last unit. And I'm going to superimpose on that when sine x is equal to -1/2. So I'm going to try and reset my zeros one moment. So you can see my line at y equals -1/2. And the graph actually crosses the sine graph a number of times. And we want to talk about a general solution to represent that. What you might be able to see is that the points of intersection occur in the next local trough, and it would occur in the next local trough going the other way as well. And that's why we want to express our answers in a slightly different format. We want to say that x equals 7 pi over 6 plus n times 2 pi, or x equals 11 pi over 6, I guess it's, and 11 pi over 6 plus n times 2 pi, where n is any whole number of powers of, or any whole number, positive or negative, that moves us up and down the screen. Why does it work? It's because of the period. The period of this graph is 2 pi, so we're going to come back and want to be concerned about the period value again. So sliding down. So there are two graphs that you can build, two graphical approaches. You can solve cosine x minus 0.75 to be equal to 0, to say cosine x equals 0.75. And then you can graph y equals cosine x and y equals 0.75 and see where those graphs intersect. So that would be the intersection method. The other thing you could do is graph the equation as it was presented. Make a y equals statement and find the x-intercepts. So I'm going to get both those graphs. So working with the same observation, that graph would repeat every 2 pi. So I could say that the general solution is that first intersection point plus 2 pi and the second intersection point plus 2 pi. We just need to take a look at that second graph, and we actually should expect that the graph crosses at 0.72 and 5.56. Let's check it out. So using this method, I find the x-intercepts, and they're at 0.72 and 5.56, and they would repeat every 2 pi as well. So that allows me to present that general solution. Let's try a couple more. So starting this one off, 2 cosine x, now I'm asked to do it algebraically, equals root 3. Cosine x equals root 3 over 2. And I'm going to go inverse cosine to find the angle. And remember, I'm making use of my CAST rule as well as my new repetition of period. The general solution can be determined by adding or subtracting multiples of the period. So we want to start recognizing again. Period here is pi. So working in radians, I think my calculator was inverse cosine of root 3 over 2. Now that should be a special angle that you recognize. So root 3 divided by 2 is 0.52. So coming from my unit circle, I should recognize that as pi over 6. So that's pi over 6 in quadrant number 1, which I can add 2 pi times n2. And then I need that difference angle in quadrant number 4, which is pi over 6. That would be 11 pi over 6 from your unit circle plus 2 pi times n. Remember, your n value is an element of the integer, so a whole number, positive or negative. In some cases, we get really weird answers, like when sine x and cosine x equals 0. When does that happen? Sorry, sine to the minus 1 of 0 is 0 degrees. When else does that happen? An inverse cosine of 0 is pi, actually pi over 2. So cosine to the minus 1 of 0 is pi over 2. When else does that happen? You might remember your unit circle, and in your unit circle, how do these play out? These solutions are unique in the period of a sine or cosine graph. They only happen twice in 2 pi, and they differ by pi. Remember what that graph looks like. Your x-intercepts differ by pi because your full period is 2 pi. So a bit of an anomaly there. So this is a strange one, but one that you should expect nonetheless. Now, what if we do it on a more restricted domain? Let's try a couple. So just talking through my work, 2 sine x equals root 2. Sine x would equal root 2 over 2. And then I'm going to go inverse sine of root 2 over 2. And you should probably recognize that. Here we get to work in degrees, so that's kind of nice. I'm looking for a restricted domain. I'm only going from 360 to 720. And when I go inverse sine of root 2 over 2, I actually get x to be 45 degrees. Well, 45 degrees occurs in quadrant number 1 and also in quadrant number 2, where I get 45 degrees, but I have to be greater than 360. So I'm going to have answers that are 360 plus 45. So that's 405. Can I add another 360 to that? Remember, we're working up to 720, and we're looking at answers that vary by 2 pi. So I go around to 45, complete a circle, go around again. I go around to the 45 here. Now the 45 there is 180 minus 35, minus 45, which is 135, which doesn't fit in my range. Add 360 to that. So that's 495. And then if I add another 360, I've exceeded my limit. So there are only 2 possible answers, 405 and 495. And they came from adding 45 plus 360 and 135 plus 360. This one's working in radians and cotangents, so probably a good one to run. I'll set her up. So cotangent of x is going to equal to negative 1 over root 3. And that's 1 over tan x. I actually need to have tan x in the numerator position. So I'm going to play the trick of flipping both sides. So now I have tan x is equal to root 3. What special trig ratio is that? Remember, I've got a negative come around. One moment, please. So this is my of pi over 3, or negative pi over 3, I guess, as a rotation angle. I'm only supposed to have angles that go from negative pi to 0. So where's negative pi and where's 0? Pi. So this is negative pi, and negative pi to 0 is up here in this quadrant. Where else is tan negative? Negative, actually only over here. So that's pi over 3 in quadrant number 2. Take pi and subtract pi over 3. So that's 2 pi over 3 living in quadrant number 2. Now I just have to wrestle as to what answer should it be. Should it be minus pi over 3? So minus pi over 3 was one possible answer, or 2 pi over 3. I've got to take a look at my domain, and my domain says I have to be greater than negative pi, but less than 0. So that actually means I'm referencing in here. This is where I need to reference. That's going to take my semicircle away from the top. So I did have two possible answers, pi over 3 as a reference in quadrant number 2, or pi over 3 as a reference in quadrant number 4. I need to take that quadrant number 4 answer, and negative pi over 3 is my answer. So the lesson will follow similar habits to what you saw here. Not a lot of new material other than the period manipulation and some restricted domain. We're going to take a look at one more lesson today, and that is factoring with trigonometric equations. A very fun application. Stay tuned.